where are we? Oh shit, not this one. Wait. Wait. Why is this not working? Wrong one. Okay. Work. Okay. Finally. So this one and this one. Wait, what? Or maybe. Okay. Not sure why this is huge. Anyway. Wait, this is weird. Anyway, I guess this works. Okay. Let's get back. So any question from this time? So we are talking about linear transformation. Today we'll finish chapter 4 and go to chapter 5. Okay. And also Wednesday is a sports day, so we'll skip class a little bit this week. But guess we will still have our problem set out on Wednesday, and yeah. Okay, so let's get back to linear transformation and a quick review of what we are doing. Okay, so 4.2, we are saying that every linear transformation we can represent it by a matrix. So we start with this Rn to Rn example, and we see that when in linear transformation from Rn to Rn, you can write it as the transformation is just A times X. So a matrix times your vector. And how you find this matrix is you find out that every column of the matrix is just you take the basis vector of the. Okay, so this is Rn to Rn. So you just take your standard basis of your Rn, and the result is the column vector of your transformation matrix one by one. And then we see that you can do this to different space. And you can also write down matrix representation of any linear transformation on any space with a basis. Okay, so if you can find order basis on V and order basis on W, then you can basically map V and W to Rn and Rn by saying that every vector inside V and every vector inside W can have this unique coordinate representation. And you just find out how the coordinate is getting mapped by this matrix A. And yeah, so once again, you want to find the column of A, then you find what the basis of what each of the basis vector get mapped to. And yeah, so you find so the column of A is the jth column of A is you map the you map the jth basis element of this E, and So that becomes some vector inside W, and then you find out the coordinate of that vector inside W. Yeah. And then we have a special example of when your V and W are actually something Rn and Rm. Okay, so but this is different from the starting Rn to Rm because we choose different bases for Rn and Rm. Okay, and then you can find this Aj by, as we said, by mapping the bases of bases of Rn, and then you want to find so that will be a vector in terms of standard basis in Rm, and you want to find the coordinate in terms of f. Then you apply this b minus 1. Okay, so that's 4.2. No question, then let's go to 4.3. Okay, so 4.3 is, well, it's just a little extra structure we can talk about the matrix. Okay, so basically what we are thinking is, okay, so it's clear to similar to this thing. We are thinking we have this Rn to Rn thing, and obviously you see that the matrix A you find depend on the basis you choose. Okay. And then you might want to ask, okay, so every basis E and F you choose here, you get a different different matrix A here, and then you want to ask, is there some relationship between those different A, those different representation of A, that's related to different bases E and F. And but we actually restrict our attention a little bit, so we restrict it to linear operator. So once again, remember linear operator means that the beginning space and the end space is the same space V. Okay, so we are saying we are mapping on the same. Okay, so it's a little confusing, but anyway, so we are mapping from V to V. Okay, so basically we are mapping from Rn back to itself, Rn back to Rn. Okay. And then we can have this E and F being the same basis because, well, you are back Rn back to Rn, then it makes sense that you just choose one basis for your starting and end. Okay, and in that case, then the matrix representation of your linear operator L will obviously once again will depend on the basis you choose, but you will see that. You will see that every one of those representations, so you choose a basis, you will get one representation, and then we see that all the representations are related to somewhere. Okay, and the basic spoiler, so you will have some S that change from so you will have some matrix S that change from standard basis to your whatever other basis. And then we'll apply A, and then you will have some S minus 1 go from your change basis back to standard basis, something like that. So yeah, so basically you are going to sandwich your A with S and S minus 1. Okay, that's really all 4.3 is about. You say similar matrix is B equal to. Okay, I'm forgetting the order, but we'll see. So it will between S and S minus 1 in some order. But anyway, let's see an example first. So what we are doing. So we want the linear operator. So so we want something that transforms from some Rn to itself. So let's have an easy example of R2 to R2. Yeah. And so we have a quite arbitrary operator here. So L of x equal to the x1 and the x1 plus x2. So L of E1, so now we want to find the matrix of L. And as we say, we just put the basis element inside. Okay, so let's see L in standard basis first. So L of E1 then is 2 and 1, and L of E2 is no x2 here and 1 x2 here. So it's 0 and 1. Yeah. Okay, and so in the standard basis, our linear transform matrix A is just 2, 1 and 0, 1, like we know in 4.2. Yeah. And then okay, so it's also like in 4.2. So now we change the basis. We want to say starting and end. We want to use these bases U1 and U2, and they are weird vector. They are 1, 1 and -1, 1. Yeah. And And so as we say, we want to find what the U1 got mapped into and the U1 got mapped into. Okay, and well, then you can either apply this A because it's already standard basis, or you can do this thing, it's the same. Okay, and anyway, L of U1 you will get a 2, 2, and L of U2 you will get minus 2, 1. Okay. And okay, but this what the U1 and the U2 got maybe into in terms of standard basis. Then we want to take those two vectors to the U1, U2 basis. Okay. Okay, so we want to find what are the coordinates of those two vectors in terms of U1, U2 basis, and as we say, then we want to find the transition back from we want to find the transition from E1, E2 to U1, U2. So that's the inverse of the transition from U1, U2 to E1, E2, which is just so transition from U1, U2 to E1, E2 is just this matrix that you list U1 and U2 here, U1 and U2. And then we know the transition back is the inverse of this matrix. And here we skip the calculating inverse. Yeah, here is the inverse. This you can probably find with Kramer formula. Okay, and yeah, then we apply this U minus 1 on the two vectors we found, and we found the coordinate in terms of U1, U2. Okay, so it is 2, 0 and minus 1, 1. Okay. So we know L map U1 to 2U1 plus 0 U2. L map U2 to minus 1 U1 plus U2. So the matrix representation in terms of U1, U2 is just this. Oh, okay, yeah. It is 2, 0 and minus 1, 1. Okay. This is a bit confusing. Yeah. Okay, and yeah, so this is what we want to do, and we want to write this in a bit more complex way, and we see that this is what we are doing. So this new matrix B is U minus 1 AU, where U is the matrix that you get by listing the U1, U2 together. Okay. And let's go back to see the derivation a little more. Okay, so how do we find the 2, 0 is we apply U minus 1 on L of U1, and L of U1 is in standard basis A of U1. Okay. And yeah, and as we say, then the second vector minus 1, 1 is U minus 1 on L of U2, and L of U2 is A U2. Okay. So this whole basis is you put this as first column and this as second column, so like this. So U minus 1 AU1, U minus 1 AU2. And but then you can think of this as some linearity. And so you can take out the U minus 1 A out. Okay. So it's like U minus 1 A on this U1 first column, U2 second column matrix. And then we know this U1 first column, U2 second column matrix is just U. Okay. And yeah, so as I said, this is really just what this equation is about. So if you change it to a basis U, then your linear transform matrix changes from A to this U minus 1 AU. Okay. And yeah, so here is the conclusion. If B is a matrix representing L with U1, U2, and A is in standard basis, and U be the matrix that just lists U1 and U2 here, and B equal to U minus 1 AU. And really you see that, so we do this in R2, but you can easily see that it's generalized to Rn. You just list more U here to E. So you just list all your basis elements to this U, and actually you change the name to S. Okay. Okay. So if you have, yeah. Oh, okay. And also we are changing from not standard basis, but basically the same thing. Okay. So, okay, this is a little boring. But yeah, so we say that we have two bases. So we have basis E and F. E with those V1 to Vn, FF W1 to Wn, and okay, and then if we have A being a representative of E, and we want to go from and we have a linear operator from this m-dimensional space back to itself. Then we have a representation on E. We want to find a representation on F. Then we just do this new representation equal to S minus 1 AS, where S is the transition from F to E. Okay. And yeah, so say if E is standard basis, then this S is just you listing all the vectors here. Okay. And okay. Any question about this theorem? So this theorem is basically doing this thing in more abstract way. So it's a little boring. So let's try to go do this really quick. So okay, so we are just doing the same thing and in a lot of algebra. Okay. So if X is any vector in Rn, okay, and so we can write X in terms of V. Okay. And we have S being transition matrix from F to E. Okay. Okay, and let's see what we do. And then we have y equal to, let's see. Okay, so we write S in terms of first, and then we do use this transition matrix to find its representation in E. Okay, so we have this y equal to S of x, so y1 to yn. Okay. And okay. So we map this back into coordinate in F, and then we apply A on Y. So we do linear transformation in terms of E, because this is how we do. Okay, and I do have B here. I think this is. I think this B is mistake here. Okay. Z equal to B of x. Oh, never mind. Okay, so the B is the linear transformation we have. Okay, and okay. Here represent the L. Okay, so we have our A and B. Okay, so see this easier. Okay, so B is you change from V to V in basis F, and A is what we know. So A is transition in basis E, and B is transition in basis F. Okay, so let's see what we have. So we have, let's write down more things here. Okay, so it's annoying. So we have x here, okay? So we have x vector here. X vector here, and we have a y vector here, and we have z vector here. Okay, so z equal to bx, and we have t equal to ay, t equal to ay. Okay, what we want to do. Okay, and so t equal to so annoying. Yo, v. Okay, so t equal to this in terms of, okay, so T is LOV in terms of E, and Z is LOV in terms of F. Okay, so those things are the same vector, but in the E coordinate and in the F coordinate. And okay, and so we say you can get Z by applying S minus 1 of T. Okay. So because you have this line here, and so this is also equal to S minus 1 of T. Okay. Because they are the same vector. Okay. So Y equal to S of X. Okay. And also T equal to S of Z, so you can get back S equal to S minus 1 of T. And okay, so I think finally we have everything together. And yeah, so S minus 1 of T equal to Z. And so we write out everything. So then, okay. And so we have a Bx equal to S minus 1 of Ay. This we have. Bx equal to S minus 1 of Ay, and also y equal to S of x. So we have S minus 1 as of x equal to Bx, and this should be true for every x. And so we say that this S minus 1 as equal to B. Okay. So yeah, so this is really a long way around, but finally we string everything together and we find this B equal to S minus 1 as. Okay, any question? Yeah, so let's write this here and it will be a little clear. So Z equal to ms1t and equal to S minus 1 Ay equal to S minus 1 as x. Okay, and x is everything. So in particular, x equal to every basis element. So so if these two are the same for every x, then B should equal to S minus 1 as. Okay. Okay. And anyway, so this is what we are talking about in this section. So we say A and B are similar if there are some s such that B equal to S minus 1 as. Okay. And also you can take this around. So S obviously is non-singular, that's why you can write S minus 1. Okay, so A and B are similar if B equal to S minus 1 as. That means if A is a linear transform, then B is a linear transform in another basis. In this basis related by matrix S. Okay, and and also you can just make things in other way, right? So you can write B equal to S minus 1 as and A equal to S minus 1 B. And S is S minus 1 to a minus 1. So so you see that A is also similar to B. Okay. So similar is a symmetric relationship because you have another S here being S minus 1. So you can think S minus 1 is like S prime. So A is S prime minus 1, B is S prime. Okay. So A is also similar to B. So the similarity is a symmetric relationship, and we just say A and B are similar. Okay. Okay. And let's see more example. So we have some linear transformation from R3 to R3, and in standard basis we have this A here. And and then we just find whatever representation. So again, this is y1, y2, y3, and it's a basis. And as we said, then we want to find a representation in terms of y1, y2, y3. So that should be that S minus 1 is where S is just listing this thing together. But let's do this slower once again. So we do this in standard way. So you found L of y1, and you apply the matrix here, and you find S here is 0. So this linear transformation has non-trivial normal space because apply on y1 it becomes 0. Okay? And then on y2 you find this thing, and on y3 you find this thing, so we actually have our example peaking very nicely because you find out that they are exactly as a linear combination of y1 into y3. Because this is 0, then obviously it's all 0. And then this thing you find out that is exactly y2, and this is exactly 4 times y3. Okay? And so actually we find out that we don't need to do anything hard to do the inverse transformation part. So we don't even need to find the y minus 1 here. Then we find out that our transformation has this nice form. It's this diagonal form. So it's a 0, 1, 4 on diagonal, and a 0 everywhere else. Okay? And this is something we'll do more in chapter 6, where we want to find the diagonal representation of a matrix or a linear operation. But that's for later. Anyway, we found out that in terms of y1, y2, y3, the L has a very nice representation. So y1 mapped to y1 itself, although with a zero multiplier, and y2 mapped to 1 times y2, and y3 mapped to 4 times y3. Okay, it's a nice representation. And also you can verify it through the brute force calculation. So if you have a here, and then you can list y here as this matrix, and if you find the y minus 1, and then you can do the order multiplication and find out that this s minus 1 is this diagonal matrix. Okay. And so this is really what we have in 4.3. So we have two matrices A and B, and so we have A being the matrix in terms of basis E, and B in terms of basis F, and S, and we have this S being transition from F to V. Then you can calculate B as, then you transition to E, then you calculate A, then transition back. So B equal to S, okay, S minus 1 AS. But when we resolve calculation, we actually go from right to left. Okay, and if A and B can be written in this way, then we say A and B are similar. Okay, any question? If not, okay, then that's for linear transformation. And now we need to kind of reset our mind and go to a totally different topic. We actually go to geometry now. We go to orthogonality. Okay. Let's pause a little bit. Chapter 5. Okay, so now we want to talk about geometry of a linear space. So we have talked about what the basis, what the dimension of a vector space. That are all ideas that we are familiar in R2 and R3. And but another idea we have about vectors in R2 and R3 is some vectors are orthogonal, right? Yeah. And now we will talk about what is orthogonal in general basis, in general vector space, and it will be a generalization from what we think about being orthogonal in R2 and R3. So what we mean is that some vector in two vector in R2. So this vector and this vector. So maybe like this, right? So we think about vector in R2, then we can think about what's like the angle theta here, and then we can say if theta is pi over 2 is orthogonal, and we also think about what is like the orthogonal projection of this vector onto the other vector. So we have x and y here, right? And okay, but as a start, let's talk about scalar product. Okay, and so we already defined scalar product or inner product. Oh wait, why do I say matrix here? Inner product. Sorry, inner product. Okay, so scalar product or inner product is defined this way. Okay, but it's a bit funny. So I think in chapter 1 we define scalar product as the product between a row vector and a column vector. But here we define as the two column vector of same dimension. Okay? And it's really, yeah, it's like a really trivial distinction. But here the scalar product we are defining on two column vector, and so we define on two column vector x and y. And well, it's a two column vector, and you do scalar product between them, and it will become a number. And hopefully you learn this in high school. So you have x with its coordinate x1 to xn, and y has its coordinate y1 to yn in standard basis. And okay, so for now we talk about everything in standard basis. Okay. We will probably do changeable basis later. Okay. So everything is standard basis, and x just have those standard coordinate x1 to xn, and y has those coordinate y1 to yn. And we define the inner product as just you take the transpose of x, so it becomes a row vector, and so you have this row vector times column vector. Okay, so row vector inner product with column vector, row vector times column vector, and you do matrix multiplication rule, and find out that's x1 y1 plus x2 y2 all the way to xn plus yn. Okay? So this standard product, this scalar product and or inner product you probably see in high school. Okay, and okay, and let's see an example. X and y, so you have 3 number here. So in R3 you have 3 number here, 3 number here, and then you do scalar product between them, and you have 3 times 4 plus minus 2 times 3 plus 1 times 2, and there is some number, and there is 8. Okay, so that's scalar product, and we'll use scalar product to define the angle between our matrix, our vector x and y. And okay, and here there is something very stupid here, but so just remind you. Okay, and okay, so as we say, so we are thinking about all these vector x and y are both in both column vectors. Okay, so later we will do a lot of stupid thing. That is because sometimes you want to take a scalar product of like the row vector and the column vector. Okay, so you think it's defined, but actually in terms of this it's not defined. So we will do a lot of you transpose this row vector into a column vector, and say we have the okay, so say you have, you will transpose this row vector into a column vector, then say we take a scalar product of the transposed row vector with the column vector, but really you are just doing the multiplication of the original row vector and the column vector. Okay. So that's a bit dumb, but that's what we'll do, and we'll try to make it a little less awkward later. Yeah. So you will say you take the transpose of transpose, scalar product of this thing with y, something like this. Okay. And anyway, let's back to actually talk about a scalar product. Okay. And okay, so the first good thing about scalar product is they tell us about the length of a vector. And I guess in more general vector space it will be like a definition of length. But for now we can see this as like this is in R2 and R3. This is just what we know. because in R2 and R3 we know the length of vector is we have those geometric rules. Okay, so in R2 and R3 we know the length should be square root of x1 squared plus x2 squared, or square root of x1 squared plus x2 squared plus x3 squared. Okay. And yeah, but this x1 squared plus x2 squared is the inner product of x with itself, right? Because inner product is this x1 y1 plus x2 y2 plus all the way to xn yn, and if the y1 y2 to yn equal to x1 x2 to xn, then just x1 squared plus x2 squared to the xn squared. Okay? So in R2, this x1 squared plus x2 squared is the inner product of your vector x with itself, and the same thing in R3. So we see that this length of vector, which we write in this notation, is known of x, is the square root of your inner product. Okay, question? And yeah, so that's the first thing we know from scalar product. So scalar product taking square root is the length of vector, at least in R2 and R3. And we'll just define this as the length of vector in any Rn later. Okay. And then also what about the angle? Okay. As we say, we'll use scalar product to define angle. Okay. But okay, so it's all still in R2 and R3, so we know angle. So we have two vectors x and y here, and want to know the angle. Okay, before we know the angle, we want to know the distance between those 2 points. Okay, and so we have vector y, vector x, and then what about this vector from endpoint of x to endpoint of y, and that will be the vector y minus x. Okay. This is a standard vector thing. I guess this is what you learn in high school. Okay. But it's also easy to verify. So I guess you can verify just by geometry in R2 and R3. So yeah, so the x coordinate of this thing should be y1 minus yx1, and the y coordinate of this thing should be y2 minus x2, etc. So this is y minus x. Okay. And so we can define, then we can take the length of this thing that we just know, right? So length of this y minus x can be written in this way, and there will be an inner product square root of x minus y. Okay, so x minus y is same as y minus x. So length of y minus x is same as length of x minus y. Okay. Okay, so we have the distance between two vectors is known x minus y, and which also equal to known y minus x, because obviously known doesn't care about minus sign. Okay, and so let's see some example. So x is this vector 3, 4, and y is this vector minus 1, 7. And so the distance between, so the difference between them, so a vector from x to y is this y vector minus x vector, so this minus 1 minus 3 equal minus 4, 7 minus 4 equal to 3. And but the length of this thing is 4 squared plus square root of 4 squared plus 3 squared equal to 5. Okay, nice number here. And okay, so now we know this length, and finally we can calculate the angle here. Okay, and then we will do the calculation, and we find out that the inner product of x and y told you as the angle. Okay, because inner product between x and y is the length of x times the length of y, and times the cosine of this angle theta. Okay, and you might or might not learn this in high school, but let's derive this once again. Okay, so anyway, but here you see that how you know the angle from inner product, because if you can calculate inner product between x and y, and you can also calculate x known and y known. Then you can divide those two to this side. Then you know cosine theta, and you can do combine inverse to find your theta here. Okay. But let's do the proof now. Okay. Okay. So the proof use the law of cosine, and we'll just assume that this is true. So law of cosine saying that the length of this thing, that's why we keep talking about y minus x. Okay, so length square of this y minus x equal to length of x square, length of y square minus twice length x, length y, and cosine theta. Okay, so this is the law of cosine. Law of cosine talking about length of this thing. Okay, so this is triangle equality. Length of this thing square equal to a square plus b square minus 2ab cosine theta. Okay. I guess usually in high school it says c square equal to a square plus b square minus 2ab cosine theta. And anyway, we care about this ab cosine theta part. So xy cosine theta part. X length, y length, cosine theta part, and we can move things around, and it should be, so you move this here and divide everything by 2, so you have x squared, y squared, and minus your y minus x squared. Okay. And then we expand all your y minus x squared into our inner product. Okay. So this is the inner product of y minus x with itself. So then that's y minus x transpose with y minus x. Okay. And then we see this thing as a matrix multiplication. The matrix multiplication has all those distributed rule. Okay. So that's yty minus xty and minus ytx and minus xt plus xtx. Okay. So you have a distributed rule on matrix multiplication. And then you remember x squared equal to this xtx and y squared equal to yty. So those four terms, so those things two get cancelled out, and finally you are left with ytx and xty. Okay. Okay. So you have ytx plus xty, but remember xty and ytx are actually all numbers, and they are actually the same number, right? Because both of them equal to x1 y1 plus x2 y2 to x and y. Okay. That's easy to prove. Okay. So xty equal to ytx, and so we just have twice xty, and so it's xty here. Okay. And so this is what we want to prove. So inner product between x and y equal to x length times y length times cosine theta. Okay, so question. That's how we use inner product to find angle. Okay, and then we back to talk about more geometry on R2, R3. Okay. And so one thing we like to do with vector is we want to normalize them. Okay. So say we have whatever vector that's not zero here, and then we can normalize it to find a unit vector u. Okay. So it's some vector that's proportional to x but has length 1. That's why you call it unit vector. Unit vector has length 1. So we just divide x by its length, and it becomes a unit vector that basically only have information about direction of x, but forgot about length of x you already divide out. Okay. And okay. So you can find this unit vector of x, and obviously you can also find a unit vector of y, and let's call it v. And so one good thing about this unit vector is then you can express the angle between x and y a little better. Okay. So as we said, the cosine theta is the inner product of x and y divided by length of x, length of y, and then you can think about this is x transpose divided by x times y divided by y, length y, and so that's ut times v. Okay. And I guess that makes sense because instead of these two vector arbitrary lengths, then we are saying then what about the inner product between a vector of length 1 and a vector of length 1 here. Okay. And yeah, so the inner product between those two vector of length 1 will be the cosine theta. Okay. You can have a u here and a v here. Okay, so that's a unit vector, and let's see this in some example. Okay. So we have a vector x. I think it's the same example. So x is 3, 4, and y is 1 minus 7. And so we can find the direction of those two vectors. So you normalize x and normalize y. And so length of x is this 5 because 3 squared plus 4 squared equal to 5 squared. So length of x equal to 5. And so you normalize x by dividing 5. So you have this 3 over 5 and 4.4 over 5. And the length of y is, okay, it's more complicated. It's square root of 1 plus 49. So square root of 50 equal to 5 square root 2. And anyway, then you normalize y and you find this is minus 1 over 5 square root 2 and 7 over 5 square root 2. And as we said, the cosine theta between those two things should be inner product between this vector and this vector. And it's quite complicated, but we set up the number nicely, so the angle is actually not too bad. But anyway, let's see the inner product. 3 over 5 times minus 1 over 5 square root 2 plus 4 over 5 times 7 over square root 5 over 2. So we have 25 times square root 2 on the bottom here, then on top we have 28 minus 3, so 25. So 25 cancel out nicely, and it's 1 over square root 2. Okay. And cosine theta equal to 1 over square root 2, and the angle is pi over 4, or 45 degrees. Okay. Equation. And if not, then we have inequality that you can also prove algebraically. Okay. So we have that x and y are vectors in R2 and R3. Then the norm of the inner product is less than the norm of x and the norm of y. Okay. And it holds if and only if either one of them is 0 or, I guess it is the same thing. Right? So one vector is a multiple of each other, and if one of them is 0, means that vector is a 0 multiple of the other. Okay. And yeah, so the proof is from xty equal to x norm times y norm times cosine theta. And anyone want to answer why this already give us this? Okay. And yeah, and you can prove this by just taking norm on both sides. And those two things are already positive real numbers, so take them out, and then you just have those two things times the norm of cosine, and you know norm of cosine is less than or equal to 1. Okay. And okay, I guess we can go a little more. And finally, we can now talk about what's orthogonal that we say we'll do at the start of this chapter. Okay. So orthogonal means the inner product equals 0. Because inner product 0 means cosine theta equals 0. And cosine theta equals 0 means theta equals pi over 2. Okay. So yeah. So orthogonal means inner product equals 0. And so some example. The vector 0 is orthogonal to everything. It's kind of a special case. Okay? Because everything inner product with all 0 vector is 0. And also those two vectors are orthogonal. So 3, 2 and minus 4, 6. Because you do inner product between them, that's minus 12 plus 12. And that's equal to 0. And also the vector 2 minus 3, 1 and the vector 1, 1, 1 are orthogonal in R3. goes into inner product, and that's 2 minus 3 plus 1, and that's 0. Okay, and I think it's nice time to take a break right now. So let's take a break, and we'll start with this projection next class.技术课，今年的啊，怎么？对，对，好，谢谢。我是不是应该翻出来？应该是你说的，我还想说，就是如果万一。哦，你是那个有挑出来的同学是不是？我算一对，好，没关系，继续讲。对，哦，就是你是那个说他不在 RN 里面的人。对，的确是课本没有讲清楚，我直接抄下来。对，所以我算一对。你没有拿考卷吗？考卷，他们考卷没还你是不是 ？OK， 好。
Yeah, I want to know whether it's the midterm small test is how yet.
Let's go. I actually don't know because the TAs are doing it, but they should be done soonish. Yeah. So, so what you want to know? You want to know the midterm score?
Yeah.
It should be, well, if it's just a score, it should be done soon. But yeah, I will ask them. Yeah.
Okay.
Yeah. We should be close to finishing grading. Yeah.
Within this week? Or...
Yeah, this week should be fine. Yeah.应该要快了，我再催一下助教他们。对，上个礼拜他们就能改差不多那个，对，所以对啊，就是其实我没办法保证原助教来改，但是应该快了。助教。 Okay. I think the time of our break is up. Okay, so let's keep go back to talking about geometry in R2 and R3. And any questions so far? So yeah, so we are now talking about geometry through inner product. And the biggest thing we know right now is that two vectors are orthogonal if their inner product is 0. And that's the result of well, that's all coming from knowing this big theorem of how you calculate angle between two vectors is the inner product between them is the length of vector, first vector, length of second vector times cosine theta. Okay, so this thing we are going to use them a lot. So now we are exactly going to use them. Okay, so the other thing we want to do, those vectors, is we want to find a orthogonal projection of one vector onto another vector. So we have a vector x here and a vector y here with some direction. And we want to find a component of x in y direction and another component that's orthogonal to y. Okay. So yeah, so now we know what's orthogonal, and we can talk about what's the component orthogonal to y. Okay. And yeah, so what's this component p that's in direction of y, and what's this component z that's orthogonal to y. Okay. And anyway, so let's find the p. So p is some alpha times the unit vector of y. Okay. So p has length alpha and direction u obviously equal to this normalization of y. Okay, so what is alpha? And what is alpha we can do with geometry. Okay. So we go with the definition of a cosine theta. So the length of x times cosine theta should be length of p. Okay. Just because that's what cosine theta is. Cosine theta is this length divided by this length. Okay, so theta here, cosine theta. So length of x times cosine theta equal to alpha. Okay. Length of x times cosine theta equal to alpha. So, and well, and then we want to express cosine theta in terms of inner product. And so here we know x times y times cosine theta equal to inner product. So we have we multiply y, then we multiply y and divide by y. Sorry, I should say multiply by y length and divide by y length. And so the upper thing, then just the thing we showed before. So x length times y length times cosine theta. This is x inner product with y, and this is divided by y. Okay. And I guess a little easier way to remember this is x inner product with the unit vector of y. Okay. Yeah. Okay. And okay, so then this alpha is called the scalar projection of x onto y. Yeah, and this is called scalar projection of x on y. So it's x projection onto y and its length. And also we want to know the vector projection of x onto y. That's this whole vector p. And then we know it's just alpha u. Excuse me. So alpha u is alpha and u is y normalized. Y divided by the length of y. Excuse me. And anyway, alpha is this thing, so it's xty and divided by y, and then you have another y divided by y. And so that's xty divided by y squared y. And so that's xt divided by y. Xty divided by yty y. Okay. So those formulas are useful. You can, guys, if you want to memorize them a little bit so that you can. Yeah, so that you can use them when you need it. Okay. And yeah. Yeah. So that's the vector projection. Any question? I guess we can do another derivation here really quickly. So we can also use not going to angle theta, we can just use the orthogonal. So z is orthogonal to, we know z is orthogonal to y, so z is also orthogonal to u. So we know either z being x minus a what u. So we have ut z equal to 0 equal to ut x minus alpha, because u is a unit vector, so utu equal to 1. Okay. And so then we have alpha equal to utx, which is also equal to xtu. Okay. And yeah, then you just have p equal to alpha u. Okay. So that's a projection. Basically, you take the inner product of x with this u. That's the length, and then you times this u again, and that's a vector. And then if you don't want to go to u first, then we have those formula in terms of x and y. So alpha equal to xty divided by y length, and this p equal to xty divided by yty and times y. Okay. And anyway, let's see an example. So we have a line here. So we talk about geometry. So we were talking about vectors, but we can also think this y as just a line. Okay. And yeah, so we can think about a projection onto line. That's like a more geometric thing that you want to do. And so we have a line that's written as y equal to 1 over 3x. And then we have a vector 1, 4 here, and we want to find a projection of 1, 4 onto this y equal to 1 over 3x. Okay. And so then we want to express it as a vector. So first we express this y equal to 1 over 3x as multiplication of one vector, and that vector should be 3, 1, because you have anything that's a multiple of 3, 1, then y will be 1 over 3 over x. Okay? And yeah, okay, sorry. And well, then let's do the formula. Okay. So the formula, so we want to find the projection vector here, and as we say, is xty divided by yty times y. Okay. So xty, okay. So inner product of xy divided by length of y squared. Okay. And so inner product between xy is 3 times 4 equals 7, and the length of y squared equal to 3 squared plus 1 squared equal 10, and then y, as we say, is just 3, 1. Okay. And so that's 2.1 and 0.7. Okay. So that's a projection. And well, by a little geometry, then we also know the projection is the closest point. Okay. So when we find the closest point means we found the projection. Okay. And if not, then let's go a little more notation. So we say you have 2 points in R2, R3, and we just say the vector from one point to another point is this notation P1, P2. Okay. And yeah, it's a little ugly here. It's a little small here. I'm not sure you guys can see, so I should do this. Okay. Anyway, let's write a bigger version. So it's like an arrow here. So it's P1. So it's P1, P2, and arrow here. So okay. So that's a vector from point P1 to P2. Okay. And okay, so more geometry. And now with this a little bit of notation, we can want to say what's the plane in 3 space. Okay. So let's say we have a vector and a point, then we can define a space, because we can say a space is a plane is everything that goes through this point, and that's orthogonal to that vector. Okay. Let's see, we have an example here. Okay, so we have a point here, and we have some vector, and we have a plane that's everything orthogonal to this vector and pass through this point. Okay. And yeah, then we can find the equation of that. Okay. So everything that's orthogonal to your vector and pass through this point. And we find out that it's so if the points are this p of x, y, z, so we say the vector from your fixed point to your new point, and its inner product with your normal vector should be 0, because that's what we define. So back here, so you have whatever point here, p1 here, so p0 to p1, this vector should be also orthogonal to n. That's how we define this plane. Okay. Let's try to draw here. So we are saying you have whatever p1 here, and so this vector from p0 to p1 should be orthogonal to n here. So this is orthogonal. Oh, this is ugly. Let's try to draw better. We're saying this should be orthogonal. Okay. And now let's try to solve the equation. Okay. And so if n equal to ABC and p0 equal to x0, y0, 0, then okay, so we haven't right, but so the p0 to p1 vector will be x minus x0, y minus y. Or actually we have said this before, but anyway, so the p0 to p1 vector will be p minus p0. Okay, so it will be x minus x0, y minus y0, and z minus 0. Okay. And then you inner product this with ABC, then we find A of x minus x0 plus B times y minus y0 plus C times z minus z0 should equal 0. Okay. So that's algebraic representation of a plane. So this is a 2-dimensional plane that is normal to n and goes through some point x0, y0, z0. And I guess it's when you learn in high school, you probably see these things, right? So you can say a plane should probably x plus by plus cz equal to, I don't know, some constant, let's say d. Okay. And you see that those two things are similar. Just you have this extra x0, y0, z0, but if you multiply them all with it, so the d is just equal to, or I can say d is just equal to is x0 plus by0 plus cz0. Okay, so you can see this is a plane equation being another form. Okay, and okay, so let's give first a really easy example that you just plug in everything. So if you have some vector, normal vector 2, 3, 4. And you want to go through a point 2 minus 1, 3, and so every vector so vector from this 2 minus 1, 3 to any point is x minus 2, y plus y, and z minus 3, and you want this vector to be orthogonal to your normal vector, and then you have 2 times x minus 2 plus 3 times y minus 1 plus 4 times z minus 3 equals 0. So you are just plugging this formula exactly in, then you will find the plane. Okay. And okay, and now we can do something more interesting. So this is actually what this picture is about. Okay. So now we have whatever plane, and then we can find the distance from a point to the plane. But our plane is actually special, so we have the d here equal to 0. Okay. Okay. And anyway, yeah, so our p0 is can be chosen as 0, 0, 0. But anyway, so we have our plane equation here, and as we see, we can decompose it into, excuse me, yeah, we decompose it into this n vector is 1, 2, 2, and then we pick our p0 as 0, 0, 0, 0. Okay. And now have another vector that's 2, 0, 0, and now we want to find this d. Okay. And then we just do geometry again, so we have this p0 and to this vector, and we have also our normal vector here, and so we see the length, so the distance of so wait, once again, what do we want to find? Okay, so we want to find the distance of this point to this plane. Okay. So distance of this point to this plane should be like you draw a normal vector from this vector to the plane. Okay. So it's this distance, but you see that it should also equal to, so this distance should equal to your vector, this vector from p0 to your point, and the projection onto the normal vector. Okay. So we are saying, okay, so we are doing a bit of geometry here. So we are saying this distance should equal to this distance here. Okay, and then this distance we know how to do. So we have a vector that's from p0 to 2, 0, 0, and then another vector. So we have this vector, then we want to project onto this vector, and yeah, so then you can do the formula we had before. So that's x inner product with y divided by length over y, and yeah, and yeah. So first the vector, where it's from 0, 0, 0. So this vector is from p0 to point is just the point, so that's 2, 0, 0. And the inner product between 2, 0, 0 and your normal vector 1, 2, 2 is yeah, is 2, and then divide by the norm of your normal vector, and that's this 1 square, 2 square, 2 square square root, and that's 3. Okay, so it's a bit complicated, but yeah. And actually here is a bit funny. So the point p0 here can be actually chosen arbitrarily. You can just choose whatever point that's in this plane, and there are lots of points in this plane, and you should give the same result. Okay. And you can try to verify yourself why that's true. Okay. So you can pick the p0 here, then you get a slightly shorter v here, but that v projected onto n should give you the same distance, same projection, scalar projection. Okay. And okay, so that's all we have in R2 and R3. And finally, let's generalize it to Rn. And when we generalize to Rn, basically we just say, well, everything is the same. So every formula we have with inner product, we think they generalize to Rn. Okay. So for example, first of all, we have talked about calculating length through inner product, and we think that generalize to Rn. Although, yeah, so we think square root of inner product of a vector to itself is its length in Rn, and that's x1 plus x1 squared plus x2 squared plus all the way to xn squared taking square root. And well, although we cannot draw Rn, but this seems like a pretty nice generalization of length in Rn, right? And okay, so that's length. You can write length as inner product in Rn, so xtx. But I guess yeah. So the inner product is once again is defined in Rn, okay. And and you have two vector in Rn, and distance can also return as so you also take the difference of those two vectors and you calculate the norm with this formula. Okay. You can calculate the length length of the difference vector, and that's the distance between two vectors. Yeah. And Cauchy-Schwarz inequality also holds in Rn. And this is something anyway, this is something that I actually will prove later. Okay, so I'll just stay here. So xty divided by xy. So xty, so the inner product between x and y in Rn, and is actually is a non-square. Is a norm is less than x norm times y norm. Okay, so it's between -1 and 1. And we can define the angle between two vectors in Rn similarly as we have in R2 and R3, because we have this thing, so if we define this as a cosine theta, it makes sense. Cosine theta is between -1 and 1. Okay. So just a cosine theta is just xty divided by x norm and y norm. Okay. And then we can invert these to some theta between 0 and pi. Okay. And we can define unit vector similarly. It's just x divided by x norm, and that's a unit vector for x, and y divided by y norm, that's a unit vector for y. And we find out that the cosine theta, once again, is inner product between those two unit vectors. Okay. And yeah. Yeah, so the inner product tells us how to calculate the angle between two vectors. And so it's this. Just like in R2 and R3, we extend this to Rn. So inner product between two unit vectors, then that's the angle between your vectors. And then a special case of this theta is the theta equal to pi over 2. That's when the two vectors are orthogonal. And that's when the inner product between the two vectors equals 0. And we will use this symbol. I don't know how to pronounce. I guess we should pronounce this as perpendicular, so perp. Okay. Anyway, so you can see this is a pretty perpendicular symbol. So we have one line and another line that's perpendicular to each other, and that's a symbol for orthogonality. So anyway, so if two vectors are orthogonal, then we write it in this way. So x orthogonal to y. Okay, so we kind of think this vector and this vector are orthogonal. Okay, and yeah. And once again, then we can derive the Pythagorean rule for tangential vector. Now, anyway, I think this is a little circular here. But anyway, so we can calculate the norm square of x plus y, and that goes through a rule. So as we say, norm square is a vector inner product with itself. So that's xyt times xy. So xt plus yt times xy. So xtx, xty, and ytx and yty. So that's a norm square of x, norm square of y, and those two things, they are the same, although we didn't. Yeah. So as before, although we didn't state this explicitly, so x inner product with y equals y inner product with x. So that's twice of x inner product with y, and we can have some Pythagorean rule, and says that the x plus y norm square equal to x squared plus y squared if your xty equals 0. Okay. So if xy are orthogonal, then then your x vector and the y vector like this, then you have a squared plus b squared equals c squared. When your c is this triangle, this long edge of the triangle here. Okay, so I think saying if these two things are orthogonal to each other, then we show that a squared plus y squared equals c squared. But anyway, it's a bit, I guess, yeah. Okay, so that's that. Any question? Yeah. So we have defined a lot of geometry by the scalar product or the inner product. Okay. So we see that we can define length by the inner product and the distance between two vectors as the length of the distance, length as the difference between two vectors. And the most important thing, we can define angle by the cosine rule. So cosine theta is the inner product between unit vectors. So that's for R2 and R3, and we'll see those, and we just extend those to Rn. Okay. And also, we have seen that we now knowing the angle, then we can do a lot of geometric calculation on R2, R3. So, for example, we can do projection, and then we can define planes, and through its normal vector, and we can calculate the distance from a point to a plane, etc. Okay. Okay. And yeah, once again in Rn, we have the angle defined just like in R2 and R3, and so orthogonal means inner product equals 0. Okay. And okay. No question, and let's try to go a little more. Okay, so let's go to 5.2. And okay, so now things are getting funny because, well, we'll see. Well, anyway, so that's anyway, so 5.2 talking about orthogonal subspaces. So I want to talk about subspace that are orthogonal to each other, and that's very nice. Anyway, let's start with this example. So back to our matrix. So we have a matrix, and we want to think about its normal subspace. And normal subspace are those x such that ax equals 0. Okay. So whatever x here, it has ax equals 0. Okay. Okay. And so now we see why we say this definition funny. So we want to say x is orthogonal to every column of AT. Okay. But what we really want to say is x is orthogonal to rows of A. Okay. So yeah. This is why we say in this class it is funny. Okay. So the column vector of AT is the row vector of A, right? But just like it's just a syntactic difference because we want to say inner product between columns. We didn't define inner product between row vector and the column vector, but it's really the same. You just transpose this thing into a column vector, and say this column vector is has a 0 inner product with this column vector. Okay. Okay. And okay, so I will try to say it in rows, so it will be a little less confusing, I think. But anyway, from x equals 0, then we see that this x vector has a 0 inner product with every row vector here, because that's just what the matrix multiplication said. So the 0 is the inner product between this row vector and this column vector. And this 0 is the inner product between this row vector and this column vector, etc. Right? And so we see that every row vector here inner product with x equals 0. Okay? And yeah. And so because x is has a linear product has a 0 inner product to every row here, and then we know that I guess we didn't say inner product is linear, but it's easy to check. Yeah, but so it's easy to see that. So you get any linear combination of a row vector here, and the inner product with x is still 0. Okay. So linear combination of color vector of AT once again is row vector of A. Okay. Yeah. And yeah. So we see that anything in row space of A and anything in the null space of A has inner product 0. Okay. So anything Y, so it's in column space of AT, but we can just say it's a row space of A. So Y in row space of A, then okay, so this is actually easier. So we have Y x equals 0. Okay, and okay, so now notation is a little funny. So we should say this. So Y is a row vector. So Y in row of A, then Y is the inner product with x equals 0. Okay. Yeah. So this is what a good example of orthogonal space. Although I'm making the notation very confusing because we are mixing a row space and a column space. But anyway, so you're seeing everything in null of A is orthogonal to everything in this row space of A, okay, or column space of AT. Okay. And okay, so ignoring the color and the row confusing thing, then we have an example of a very interesting thing. So we have two subsets x and y. We will say they are orthogonal if every vector inside them is orthogonal. Okay. So xty equals 0 for every x in x and y in y. Okay. And if x and y are orthogonal, then we write this thing. Okay. So before we define this notation only for vectors, but we also define this for space. So we say two spaces are orthogonal to each other if every vector inside them are orthogonal. It's a very strong requirement. Okay. And yeah, so this is like a bit of extension of the rank nullity thing we had before, as we'll see more. Okay. So this null space and rank space and row space, we say that they're dimensional, add together to n. Oh, sorry, add to n, and now we see that those two spaces are also orthogonal, so they have an even stronger property. But anyway, let's go back to just seeing what's orthogonal. Let's forget about null space and row space for now. Okay. And okay. And let's have an example of two spaces that are orthogonal to each other. So x is spanned by E1 and y is spanned by E3. So x space are vector that look like this. So alpha 0, 0. Oh, actually E2, not E3. And y vectors are spanned by E2, so 0, beta 0. And you can easily check that when you take an inner product, it's 0. So everything then orthogonal, and so those two spaces are orthogonal. Okay. And you can think like even if y is spanned by E2, E3, then they're also orthogonal, right? So you have a beta here and a gamma here. So alpha 0, 0 is orthogonal to 0, beta, gamma. Okay. And that's really the idea of orthogonal space. But obviously, this is everything is in standard basis. But you can have more exact example. Okay. And but here is the example that confuses you a little bit. So two subspace might look perpendicular, but they are not orthogonal. So orthogonal is very strong. You do have basically no overlap between them. Okay. So for example, the xy plane and the yz plane looks perpendicular, but they are not orthogonal. Okay. Okay. So let's first confuse you a little bit to make this example. Okay. So we are thinking about in R3. Oh, this drawing is bad. Okay. So this example is saying that we are in R3. Okay. So you are confused by this. Hopefully this will let you less confused. And if you are not confused by this, then that's good. Okay. And anyway, so we are saying this xy plane, so xyz. So this xy plane here, right? This xy plane and yz plane. These two planes looks perpendicular to each other, but they are not orthogonal. Okay, because you can find a vector that's both in xy plane and yz plane. That's not okay. So I guess you can say you can find a vector that's in xy plane and a vector in yz plane that's not orthogonal to each other. And the example we are given is this vector and this vector. Okay. But I think a better example is just this vector here. So if we have x1 equal to x2 equal to 0, 1, 0. Okay, so this vector is both in the xy plane and in the yz plane. And if you take the inner product of it with yourself, it gives you 1. Okay. So you see that those two planes are not orthogonal to each other. And they are subspace and they look pretty perpendicular, but they are not orthogonal. So if you have an xy plane as your first space here, and you see that you should have just the z-axis as the second space. And so xy plane and the z-axis will be orthogonal to each other, but xy plane and the zy plane are not orthogonal to each other. Okay? And yeah, so be a little careful about orthogonal. Orthogonal is very strict. The two orthogonal space you need to have no overlap. That's actually a theorem we'll see later, but probably not today. Okay. And anyway, so here is our example. So example being that just is xy plane and the z-axis example. So if x is in xy plane, so it's alpha of e1 plus beta of e2, so alpha beta 0. And the vector in y is 0, 0, gamma. And now I see that they are actually orthogonal. So alpha beta 0 inner product with 0, 0, gamma. You have alpha times 0, beta times 0, 0 times gamma equals 0. So those two spaces now are orthogonal. Okay. And and now we go to a little. Okay, so this example already showed that orthogonal, but now we go to another a little more example. Okay, so now we want to find. Okay, so now we focus on this space y. Okay, so space y is. Okay, so space y are vectors of form 0, 0, gamma. Okay. And now we want to find all the vectors that are orthogonal to every vector in y. Okay. Okay. And well, y is just spanned by one vector 0, 0, 1. So if you want to be orthogonal to y, then you basically want to orthogonal to this 0, 0, 1. And then you want z1, z2, z3. So you check your z1, z2, z3 inner product is 0, 0, 1, then you see that z3 equals 0. Okay. Okay. So this is a necessary condition for your z to be orthogonal to every vector of y. And okay. then we see that these three equals 0, so it basically need to be inside this X space. So we see X is a set of vector, so we have some completion property of X. So we see X is a set of vector that's a set of all vectors that's orthogonal to Y. Okay. So here the important thing is this O here. Okay. So we know every vector in X is orthogonal to Y, and it also contains every vector that's orthogonal to Y. Okay. And so this is a special example of concept we want to talk about. That's the concept of a complement. Okay. So if you have a subspace in Rn, and then we can find the complement of your subspace. So we have some subspace Y, and then we can find the orthogonal complement. That's a set of every vector that's orthogonal to Y. Okay. And okay, so now it's just a set, but we will see that this is a subspace very soon. Okay, so yeah, so this is kind of, I don't know, everything else other than Y, but not quite. I guess this is a very good example. So if E3 here, then the complement is the space spanned by E1, E2, and say if your space is spanned by E3, E1, then the complement is spanned by E2. Okay, etc. Okay, and you can probably fill this example. So we'll see later this part. Then the dimension of complement plus the dimension of your original space equal to this n. But for now, let's talk about more thing about the complement. Okay. Okay. So an example of complement. Okay. So you have two orthogonal space, they might not be complement because complement has this requirement of O here. Okay. So you need to be every X here. So for example, if you have the first space spanned by E1 and the second space by E2, so they are orthogonal, but they are not orthogonal complement because say the complement of Y is spanned by E1, E3, and this X doesn't include E3. And also the complement of X equal to E2, E3, and this Y doesn't include E3. Okay. So complement need to be like everything else, everything orthogonal to your Y. Okay, question. Okay, and then we go back to the other remark. It's a bit funny. Okay, so we talk about complement, and now we're back to go back to this property of orthogonal subspace. Okay, so the first property that we kind of already see, and we say that if X, Y are orthogonal subspace, then X, okay. Yeah, I guess we didn't prove the complement of subspace, but you can prove yourself that the complement is actually a subspace. When are we going to? Anyway, so let's back to this remark on just orthogonal subspace. So if X, Y are orthogonal subspace, then actually it's here. What am I doing? Sorry, I got confused. Yeah, so X, Y are subspace, then X intersection with Y equals 0. Okay, so this is easy because if there is a non-trivial vector in the X intersection with Y, so it means that X inside X, big X, and X is also inside big Y, then that means the X inner product with itself is equal to 0. And yeah, and from the Rn thing, then you see that every coordinate square of X so like x1 squared plus x2 squared to xn squared sum together to 0, and that must mean to then that must mean all the coordinates equal to 0. Okay. So it's because x inside big X and x inside big Y, and everything inside big X and everything inside big Y has inner product equal to 0. And so norm square of x equals 0, then norm of x equals 0. Okay. Okay, so the first thing, and the second thing is the thing that I failed to find. Sorry. And okay. And the second thing is if Y is a subspace. Okay, and then its orthogonal complement is also a subspace. And you can just check the you can just check the closure. Okay. And so if something inside the okay, and yeah, just check closure. And so if something inside orthogonal complement, you have something inside orthogonal complement, then then you take alpha times. And okay, so we didn't prove the linearity of inner product, but you can check it by the definition easily, because just remember our inner product is so this xty equal to x1y, xty equal to x1y1 plus x2y2 plus da 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 2 plus xn 2 plus xn yn. Okay, and you can see that this thing has a lot of linearity. So you have taken alpha x, then you have alpha on every term, and you can take a lot of alpha, because this is basically just scalar addition. And scalar addition and multiplication, they have all the distributive rule, etc. Okay. So alpha x times inner product with y is just alpha of x inner product with y. And we know it, inner product of x and y equals 0, so that's alpha times 0 equals 0. And so alpha x is also orthogonal to everything in y, and so alpha x inside y. And also if x1 and x2 are element of yt, and you will see the inner product of x2, x1 with y, and then you will just this every, okay. So now we will break this x1 equal to x11 plus x21, and this is equal to x12 and x22, etc. Okay. And anyway, so we see that we will also have a inner product also respect the addition rule. And then x1 plus x2 inner product of y will be x1 inner product of y plus x2 inner product of y, and that's 0 plus 0, and that's 0. So yeah, so we also have a closure under addition, because x1 plus x2 also has is also going to everything in y, and it's inside y dual. And so we have a closure under multiplication, closure under addition, and so this y dual is a subspace. Okay. And then we have another unknown topic later, so let's stop here. I think it's a good place to stop. So any question? Otherwise we'll have stop a little early today. Okay. And yeah, so I think next time is Monday, and we'll go through this more analysis on regularity theorem. So basically we are going to say the null space and the row space are orthogonal complement to each other. Okay. Okay. And yeah, so see you next Monday.